there are probably some of you in attendance right now that would know how to model that better. You know, I haven't done a lot of that kind of modeling, so I'm not sure if CT would be a good fit for that. But anyway, we have just taken from that this program called WGEN, and we're using that as a standalone program that we, or model, a standalone model that we built in GoldSim, and that any of you can copy and paste and use it in your models. So we were just interested in that part, so we could simulate, for example, runoff on a mine site, which is a common use of this, but it could be used for a lot of other things where you're looking at flows from some sort of watershed or catchment area, but also temperature and solar radiation. So maybe you're looking at evaporation to simulate a water demand on a farm, you know, because of crop demand, things like that. It uses a first order Markov chain gamma model. I'll explain it. And then this is really just based on the probability of whether it's raining today or not. But also that output is, there's the temperature and the solar radiation are dependent also on that output. So it's driving all of the weather parameters, this output. Okay. Oh, there we go. So what we have is an initial input file that's a time series of daily precipitation. So we're just going to need that to build your inputs for WGEN. It's going to be a one-time exercise, most likely. Maybe down the road you would update it, but for the most part, this is a one-time exercise. So you kind of have to keep that in mind. That's why I have two GoldSim models. There's a WGEN PAR, which is essentially an engine, like a preprocessor, that takes your time series records and generates an input file. And then you only do that one time. As long as you have your historic records all, what's the best way to say it? You know, if you're missing a lot of data, you want to deal with that first. You know, we can't use blank values in the model. So you need to, or text file or text entries. They have to be values. So watch out for that. Clean up the data. Once that's done, then everything would just be run at one time, and that would be all you would need for WGEN PAR. So that would be the second step. You do that one time, you generate this input file, and that input file is called WGEN PAR XLSX. All of these files can be downloaded from our website, and I'll show you that at the end. Then you can run WGEN, and it just runs off of that output file, that Excel file. But you can break that link pretty easily. I'll show you how to do that, and it can become standalone. And that's kind of where you want to end up. You want to end up with the standalone WGEN that doesn't need all of this these three other steps anymore, right? And you would go and do simulations for your project. So that's the intended use of WGEN in GoldSim. Okay, so those of you that have been using this model, I hope this isn't too much review, but I just realized in my previous webinar that I needed to get a little bit more background up front of WGEN. Okay, so the way that basically, what I want to do is zoom in on the simulation of precipitation, because that's really what I'm focused on for the change that we've been making. Overall, though, it's shown on the left all of the outputs are, where they're coming from. There are 4 outputs here, and they're time series. Well, it's called, in GoldSim, it's called a time history that we are capturing. And we can do that for multiple realizations, with each realization being unique from the other and random through time on a daily time step for as whatever duration you choose. You can pick any duration, and you don't have to change any other input. You don't have to link to Excel or look at the time series record. You could pick any duration, any start time, because it's not using any time series inputs. But on the left, so it's a pretty useful, in my opinion, it's a pretty useful tool for doing any kind of forecasting of models that involve these climate outputs, temperature mainly. There are a lot of models out there that could benefit from this because it gives you a very robust and clean way to generate random rain over years that are based on the historic records, and they're all random. So it makes it a very versatile tool. You can look at any time period, going forward or backward or whatever. I mean, you'd want to go forward, obviously, but when you would start the simulation, you can pick any starting point in time. So anyway, the precip generator is here, shown on the left. From that, I told you there were dependencies in the temperature and the radiation portions. They are dependent on whether it's a wet or a dry day. So there's functions in there that take that into account. You'll see this thing called Fourier function up here. This is a way to generate a cyclic behavior to mimic seasons within a year. So that's where you get the cycles. That's how you get the cycles of temperature and radiation. And what's nice about this is, as long as it knows the site latitude on the planet, then it can produce an accurate representation of the average cyclic behaviors of temperature and solar radiation. So it only needs one input. It doesn't need monthly inputs for temperature and radiation. You just give it one value. I mean, it has, I think, 4 or so for each temperature and radiation, but you don't have to do those monthly. Precipitation is the only monthly input we provide. Okay, so inside of the precip generator, if you go in there, there's a part of here that's really important, and this is the part I'm highlighting. There's more to it, but this is what generates the randomness of whether it's going to be a wet or a dry day today. And it's just a Boolean output, a true or false, yes or no. And it's based on this PWW and PWD factor. And these are key. These are the two of the key inputs to WGEN. They're monthly, they're 12 values. They're each a vector of 12, one for each month, and they're a percent. It's a probability number. On the left, PWW, that is the probability that today is wet if yesterday was wet. PWD is what is the probability that today is wet if yesterday was dry. Okay, so most of the time, most places, PWW is larger than PWD. For all the sites I've looked at quite a few. I mean, it makes sense, right? And otherwise it wouldn't be called a, well, yeah, anyway, I haven't seen that, but what it means is once it starts raining, it'll be more likely to rain the next day. And once it's dry, it will be more likely to remain dry the next day. And that's how you get these periods of time between each rainstorm that are dry. So it's pretty good. It's a pretty good way to represent similar rain durations and gaps between the rain, so dry periods, by reading a time series of a daily input time series. So it makes sense that this would be able to mimic that, and it's a pretty simple and clean way to do it. So the way that you model it then in GoldSim well, also in the code, we just took Fortran code that was available on the web. I think we provide the link to that in this model. We do provide some links to resources from inside this GoldSim model, but we uses what's called the status element in GoldSim. This is a very clean way to do it in GoldSim because a status element is what's called a state variable. It carries state forward, which is important it's an important way to differentiate between um, um, other types of elements that we might refer to as static elements that they're not static though. I'm not using the right term, but it's a value that does not carry state. It just calculates instantaneously every time step. Provides here's an output. I just have these inputs. Here's my output. So they're different. But anyway, the status element over here on the right is called wet status. Okay, so it's going to remain whatever status it has, true or false. It's always true or false. It will carry that value as long as it needs to until it's told to change it. So it'll always carry that value. So it always has an initial state until it's changed. And so it also can be used to have a feedback between it and other outputs that it's looking at. So in this case, we could say if we know what the probability is of it being wet today, if it was wet yesterday, and the status right now is that it was wet yesterday, then we will continue with this probability number. And this is all based on a randomness, a random value between 0 and 1. And so we can go into this further if you want to see how it works. But essentially, it's just saying, okay, create periods of dry versus wet, which are simulated over time as an output called wet today. When it's going to stay true for the duration of historic periods of rain, of daily periods of rain. Okay, so we use Monte Carlo simulation in GoldSim. That's one of the big benefits of putting WGEN inside of GoldSim is because GoldSim runs Monte Carlo very nicely. So with WGEN being in here, then we can walk through the process. This is an image taken from other presentations we give when we introduce GoldSim. But for those of you that are new to doing Monte Carlo simulation, the way that it works is you have a probability distribution input, and GoldSim will, on a single realization, it will sample once or multiple times from this distribution. And as it walks through time, it will continue to resample from this distribution if it is told to do so. And then you could end up with a chart like you see on the right with the result of all of these realizations. And so that's what we have. And then you can look at probability percentile time histories that look like this one with the red. This is showing the ranges of where all of your outputs went over time and their probabilities of being in that area at any point in time. And if you took a cross-section of that, it would be a probability distribution, a PDF view, just like you see on this input over here. Okay, so that is how it works. That's what it's doing inside. And then we generate these outputs. The the 4 outputs I was talking about, this you obviously see 5 because at the very top it shows daily on the left, daily precipitation, and then period precipitation on the right. And I say period precipitation because you can look at it in either monthly or annual over the period of simulation. Now, this output is only showing 1 year, but you could run it for 10 years or whatever years. I just showed 1 because it gets pretty busy looking when you run a lot of years, and which is fine, but I didn't want that for our screen capture that we use in our article. But anyway, that's what the output of WGEN looks like. We also have in the model a little testing place where, just to make sure that we feel comfortable that we are representing the seasonality of the historic records. We're going to compare the historic records statistics versus ours from the simulation we just ran. And so here's a screen capture of what you'll see if you just run the model using the data it comes with when you download this model. This is the output. So you can see there are some differences, but over the years I've felt comfortable with this, and certainly haven't heard any complaints from anyone yet. But I'm open to criticism or any feedback on this. And you can look through this when you download the model. But I have added some outputs: dry dry days, number of dry days, and run of dry days. I added that because we show number of wet days and run of wet days, so why not dry? We should show the dry ones too, mainly because we were interested in droughts. But okay, so this is where I'm talking about how I added the dry days and the run of dry days. So this model can be copied and pasted, essentially. That's the easiest way to say it, because that's what you do. If you have a model of a system, like an actual system in the environment or something, and it's interacting with storm events in some way, or the weather, I guess, just in general, temperature too, then you could just copy and paste WGEN in your model, disconnect it from Excel. Once you do WGEN par, right? You run that once, do the preprocessor one time, and then disconnect it from all of that. And now you have a weather generator in your model. So it's pretty easy to use. And here's an example where it's being used in a simple reservoir model that supplies water to a city and farms. And then here's another example where it's tied actually to inputs from a 7-day, or maybe it was a 14-day weather forecast, where perhaps you want to look at it maybe in a little bit more detail. What are we looking at for the next 14 days, and then do a simulation based on that with some randomness because of the uncertainty of the forecast and other things. So that's the kind of uses you might see. So one of the limitations, okay, so that's where I wanted to talk about why we're looking at multi-year simulations of what WGEN. So the limitations of this model are generally when you run this model and you compare it on an annual basis. Now I'm talking about, let's sum up the annual precipitation, and let's do multiple realizations, multiple years, and now let's plot it on a distribution and compare it to historically over, let's say, in this case, the screen capture had 130 years of records of historic precip, and I just took the sums, the annual sums, put them on a distribution, that's red. Okay, and then you run WGEN and I was getting blue. And I was looking at this and I was realizing that while it provides really good information on the seasonal fluctuations and the day-to-day simulation of these outputs, it does well on those comparisons. It does not do so well on the annual fluctuations. So, so we started looking at this, and realized that if we're going to look at droughts, we're going to need to at least, at a bare minimum, we're going to need at least be able to simulate historic droughts. And so what are we going to use looking at historic records to help us understand droughts? first of all, we have to define what is the drought we're looking at. And so there's lots of different kinds of droughts out there. So I just wanted to make sure we're on the same page here. And this diagram is from if you go to drought.org, it has a lot of information about introducing you to what drought means. But we're talking about a meteorological drought here in the upper part of this chart, and just looking at precipitation. It also has temperature and solar radiation outputs, obviously, but what we're focusing on right now is just the precipitation part. And yes, they're probably tied, and there's all these other things that we could consider, but it's too complicated. So we're just looking at precipitation right now. Okay, so what we did is we, well, I should say I at this point now. So what I did is I started running WGEN PAR, that's the preprocessor model. I started looking at runs of this model when you're only using the driest 20 years on record out of 100. And then also doing runs for the 20 wettest years. And I chose 20 because in the documentation of this code, the authors recommend that you provide at least 20 years of input values to generate good WGEN outputs. And I'm talking about these outputs that are shown here in this table. These are the monthly values of PWW and PWD, which I introduced to you. Alpha and beta are used to generate the magnitude of rain on a given day when it's wet. So those are also very, very important values. But this is what it's using. These are very important. So they recommend 20 years. So that's why I chose the 20 driest years. Perhaps not much more scientific than that. But I definitely prefer to take their word for it because they took the time and effort to build this model. So that's what I'm relying on there. But in doing that, I came up with an output. Well, first I had to find the 20 wettest years and 20 driest years. So I had to do an analysis of the time series a little bit. Anyway, once I came up with that, I did those runs and I came up with these outputs. These are just charts for multiple sites where they're shown in the different colors for the different sites I looked at. Washington, Iowa, Australia Plains, Australia, Dublin, Ireland, and Logan, Utah. Those were places I found really good sets of 100 years of records without blanks, without problems, for the most part. Actually, no, I don't think any of them had issues. I think they were all good data sets. So that's why I used these sites, and they're kind of all over the world. I wish I could have found one in South America, but I couldn't. And anyway, so here they are, and I ran WGEN PAR, the preprocessor, for their driest years and wettest years, and I put those in these columns called dry and wet, as you see here. So an average just represents using all in the entire 100 years on record. That's why they're all just sitting there at 1. They all go to 1 because that is the same. Those outputs are generated there that way. So that's considered average, I suppose, because we are looking at 100 years, and that all the years impact these parameters, right? So that's why it makes sense to use the average, to assume that's the average. To assume that the driest 20 years on record, now when I say dry, I'm talking annual total precip. So that's how I measured the dry versus wet. I just sorted them. I sorted the annual precip, and I realized you could have droughts within a year. You could have perhaps a very wet winter, but then no spring or something, and no rain during the spring or something. It could be strange like that. But I wasn't looking at that. I was looking at just the annual total precipitation to determine whether it was a dry within the 20 driest years or not. Okay, so I just sorted the table. That's how I figured it out. But when you run those models, we saw consistency with all of them except for Australia, Plains Australia. So if you, I would imagine if obviously we need to do more sites. This isn't very many, but if there are any volunteers out there, people that want to run more, I would be very happy to provide you with the steps necessary to run them, and contribute to these charts, because it's useful for setting up a model that can provide similar variations. Ideally, we'd probably want to look at a probability distribution or something, but we're already trying to generate inputs of probabilities, and so it's getting a little bit, it feels like that's going too far. So that's why I tried to keep it simple. And I'm trying to keep it as simple as possible. So, but I also want it to be robust, right? I want it to be able to capture it would be nice if it could capture this oddity of Australia, Plains Australia. Why it is that in drier years, the PWW is actually greater. It's a greater value. It's greater than its average. Um, um, Whereas uh, for probability of wet after it being dry, so this is what causes us to get out of a dry period. Dry years, it went way down below the others. So maybe that makes up for this oddity of it went up actually in dry years, which means to me that during drought years in Australia, Plains Australia, during drought years, perhaps it's just got really long storms when they come. They're very infrequent, but they're longer for some reason. I don't understand. Um, but anyway, that's what we see when we do these runs. So what we can do then is we can generate a distribution of its output of the annual precipitation values, and then we can, from that, we can calculate just a normalized factor that represents the annual fluctuation from normal, so the deviance from the average over time. We can generate that using a stochastic element, and that is because we're just using what's called it's essentially using a sample distribution, just sampled from the historic. So we calculate the annual precipitation outputs, and then we just create a probability distribution using those values, and then we just sample from that. So it's just an easy way to sample from historic. Now, this already has a limitation, obviously. You're probably thinking that right now. What if we only have 20 years of historic record? In some places, that's considered a lot. So what do we do in that case? And I don't really have the answer to that very well, but you could decouple this stochastic element from the historic. You could do a rough statistical analysis in Excel or R, some other tool of your historic record, and perhaps you could fit it to a parameterized probability distribution right here, which would, I think, be defendable for sure, and definitely straightforward. So it's a possibility that we consider something like that, going that route instead, fitting it to a probability distribution. That would probably be a better way to do it. But right now it just samples from the historic record of the annuals. So what we're hoping to get is something closer. We want ultimately an output that can match both daily, monthly, and annual fluctuations through time, is where we're getting at here. We also calculate the autocorrelation of the annual values. That's really important. We're calculating the autocorrelation of the annual values as they fluctuate. That's calculated in Excel and also brought in and used in this stochastic element as an input, because you can make stochastic elements autocorrelated. So we autocorrelate it too. From that, then we will calculate these. It's just a factor that's applied to each of the PWW, PWD, alpha, beta inputs. It's a factor applied to those, and I'm happy to show more at the end. If you're interested in how I apply those factors, I'm happy to do it. I just didn't want to bog down too far, because then I wanted time for some questions, if there are any. Okay, so now I'm going to show you at these 4 different sites the difference between WGEN as it is today on the left versus WGEN with long-term factors that I've applied. And I did this running 100 realizations, each of them for 50 years. I ran the only reason I ran them for 50 years was to provide you with the idea of how, how it performs over the long period, because that's the point. That's what we're trying to get at. But we also can look at the final value in the top chart. It gives you an idea of over the 100 different possibilities out there. Here's the range. Now, it does not account for long-term climate change. Ultimately, that would be what we'd want to see in WGEN for sure. But it does this work we've done to this point. It does start us down that path. It's like a stepping stone, I think, because we now have a way to generate an input that represents something changing over multiple years, instead of just seasonal. So that would, I feel, this would be the approach we want to do. So I think that it's opening the door for that, just to make sure we're being careful in what we're generating here, and make sure we're doing it in a defendable way, right? Because we don't want to go down the path of, well, it's just uncertain, let's just put a slider on a dashboard, and let's just let the user just move it up and down a little bit until they're I mean, that could definitely be a way to go. Maybe it is, but we get people asking, well, how can you defend it? And then we might run into some difficulty there. Okay, so on the left, it says here pretty clearly, if you see I don't know if you can read it over here on the far right. I'm sorry for the small font. But the red line is just sampling historic values. And then the blue line is what we simulate in WGEN. And you can see here, this is a run we did for Washington, Iowa. And it shows that simulated did not have it didn't have a very good range on the drier end and the wetter end. So it's kind of missing, like, what I would consider drought years, very much drought years. It's missing those. It's missing a little bit of the flood years too. So what I did is I applied these factors that, and everything else is remaining the same, right? I just applied these factors that just slightly adjusted the PWW, the probability of it being wet, right? Those 2 numbers, and then this alpha and beta value. I just slightly adjusted those on an annual basis, just a one constant number for the entire year, just a little slight adjustment to it, all based on those that analysis I was showing here. So it looks at this and it says, okay. Anyway, let's not get too far into that. But anyway, they're applied on an annual basis, and you can see that the distribution looks better. I think it looks better here. Okay, so down on the bottom left corner, okay, this is the way WGEN originally was over the long term, and you can see here. Once again, the key is it's a little bit hard to read, but the red is the solid line is the average of the sampled historic record. If we're this is just all we're doing is we're running 50 years of a forecast, just randomly sampling history. That's what the red is. It just goes back and it samples one of the annual, just randomly, anywhere, randomly in the historic record, and it says this is what it is. And then if you plot these on a statistical basis where the solid red line is the mean, and then if you take the 10% of the lowest ones for all of the realizations, that's the red, the darker red dashed line on the bottom, and then the 90th percentile of all of the runs. Okay, so what you're looking at is not a single run. It's not a single realization. That's not what any single realization looks like, right? I just want to make sure that's clear. Anyway, it shows you essentially what are the wet. I'm calling them wet years. It's the 90th percentile. Okay, so if you went up here to this top chart, the 90th percentile is between the top two lines up here. So that's a good capture of the wet years, right? And same with down here. Okay, anyway, over here on the right, you can see that it's not perfect. And a reason for that, I believe, is that I'm trying to simplify, back to this, I'm trying to simplify how we adjust for a wet and a dry year. I don't want to tie it to the site that we are located at. We could generate that from a historic record. In fact, that is a way we could go, because I was looking at that site. But in a case like yours, perhaps maybe you're working on a project that isn't at a place that has a lot of good records, right? So you may not have that luxury. And so what you may be doing is wanting an input that is not just based on just one location. Maybe it's an average of some of these or something. I don't know. So that's what I did. I threw out, I'm sorry, for everywhere except Australia Plains. Not that I don't want to make them feel bad over there, but I did throw that one out in order to do a simulation that was not over there, not in Australia. Looking at these other places, I used an average of these. And so I believe that's where some of this fluctuation is coming from, but also that there is a limitation. If I go back to here, there is a limitation on just working with 100 years of records, right? There's a limitation on what you can show randomly from that. You're just sampling a 100. That you're just limited to that. That's it. Ultimately, what we would want is the ability to look at many more possibilities than just 100, right? And that would be a good way to use WGEN. You could run as many realizations as you want to get really unlikely but very very large rain events or periods of rain or very, very dry years that are less probable that you might want to look at. And that would be a good use case here. But we want to make sure we can at least mimic the historic. So anyway, what we're seeing here is that we went a little above on the wet side. It was kind of like we over projected with how these inputs were being interpreted a little bit on this Washington, Iowa, but it's not. But I would say I would feel more comfortable doing it using this one on the right. If I were doing a project for that location, I would probably feel more comfortable with the one on the right because it does at least, if you were concerned about flooding, then it's a little more conservative, I guess, but not necessarily if you're concerned about water supply. So anyway, next one is Australia Plains, Australia. So I did change the inputs so they're a function more of what you see in these charts here, these orange. I followed these paths. So I said for the 20 driest years, we're going to increase PWW for the dry years. That's the way that this model was run. I changed the inputs. and I can show you how that's done. But anyway, here's the original WGEN. You can see once again we're missing the dry and the wet years. And then if you go over to the right, you'll see that we end up at the same point. But probably because of my simplification of saying 20 driest years, 20 wettest years, right? That's a simplification of what's actually going on. There's kind of the nuance of in between and everything. So it makes sense to me that I get to the same point, but there's also a distribution of these variables. You know, it is a distribution, and my simplification is probably equivalent to a normal or to a uniform distribution. That's why you're starting to see a linear. You're seeing a linear difference through here. So that begs the question to all of you, my audience. I would be happy to hear what your opinion might be on this, of whether you believe that generating a probability distribution of essentially the annual outputs to generate parameters that we then supply. Essentially, it would be each PWW would be a sampling from a distribution that we would generate from historic record. It sounds complicated, you know. It could be done when we have all the data to do it, but it just sounds really complicated, and I was curious to see what people thought. But the outcome of a simplification of using an average over of what we considered a dry period, just one value, the result is a linear, more of a linear distribution, which is we'll have to think about what that could present. So anyway, that's what we're looking at right now. But if I go to the next site, Dublin, Ireland, you see a similar situation. Dry, it goes drier and wetter than the simulation does. Historic is drier and wetter. And then you come over here to with our long-term factors, and we're better. It does look better in this case, I think. We're not all the way there, but it's better. And then we go to the next one, Logan, Utah. Similar thing. Mostly that's shown down here in the red. And I am a little bit curious as why the red on the historic is flatlining, and I'm wondering if there's a problem with the data. What I mean is we're not getting a lot of variability in the driest years, which seems like that might be a problem with data. I'm not really sure. So anyway, in conclusion, I feel like this is definitely an improvement to WGEN, and the reason we're going down this path is, like I mentioned earlier, is for support for standardized precipitation index. But anyway, I wanted all of you to see it because I will be providing this presentation and the model where it stands in our webinar archives. I appreciate you joining, and I'm sorry that this went a little bit long. I meant it to end a few minutes ago, but I will be happy to take questions, and I will be happy to stay longer to answer if you have more questions at this time. But otherwise, thank you so much for participating, and I hope it was useful. Also, the February webinar will be by a guest speaker from WSP. You can look it up on our website. I highly recommend it. It looks like even if you don't do the kind of work they do, they're looking at Radwaste site, I think. So if you don't do that kind of work, it's still what they're doing with GoldSim seems really interesting, and I thought they were really leveraging the of what GoldSim can do for you quite well. Also doing some things with input files that were pretty complex, and I often see our customers dealing with complex input sets. So I highly recommend that you join it, even just for those reasons. All right, so thanks a lot for participating, and I'll just take any questions if you have any right now. Otherwise, I hope to see you there next month. Okay, I don't see any questions, and I've got just a few more minutes here. So what I want to do is I want to show you GoldSim, the WGEN model with the long-term factors. I'll just pick one of the sites. Okay, the model is the same regardless. This is the one that you can download, and it's actually identical. The only the only difference would be is the Excel file that it's drawing this data from. So it has a different input file than you might have when you download this, because what it does is when you download this file, this model, it comes with the Excel file and everything for the sample that it runs, which doesn't even have 100 years, by the way. It only has 20 something years. That's the one that it comes with when you download it. So what you have to do is you have to point it to your new Excel file that you generate. But anyway, the difference here in this model, if you're familiar with WGEN, all of this would look familiar to you. This is the input data. Well, except for this new change, which is this one, long-term factors. So everything else is the same. These are your 12 probability numbers I was talking about. And then if you go into long-term factors, then you'll see there's this annual stats, which is it's just drilling into the Excel file of a pivot table. That's all it is. So in Excel, there's a pivot table, which you need to make sure is up to date before you run this model. And so there is a connection to Excel right here. And if you wanted to decouple it, then you would have to come up with, that's where I was talking about this probability distribution. So if you wanted to decouple your model from the historic values, let's say you don't have very many years of record and you wanted to represent it as close as you could with just a probability distribution, then what I would do is I would come in here and go to double click on this, go to edit and change it from externally defined to, see, this is how I'm externally defined can come off of a submodel. So I'm using a submodel to read Excel. A bit complicated way to set it up, but very easy to run now. Anyway, instead of using this externally defined distribution, you could pick a different one and just a parameterized one, say log normal gamma, Pearson type 3 distribution. So there's some options there, gamma distribution. So you could just have something parameterized, and maybe you do an analysis of your records off to the side using R or Python or something, right? Then you could just fit a distribution and put that here. That would be the preferred way to do it, I think. And then you can calculate the same outputs. But in here is where I have the kind of the simplification going on. So what I do is I say, how do I normalize the long-term factor, which is just the output of this annual probability distribution divided by the mean over all the years. It's just a normalized factor, right? And so I take that normalized factor and I say, for dry years, if I have a long-term factor of 0.7 for dry years, that means it's going to be 0.9 of average of the PWW, and that's just based on a visual inspection of this, looking at where the average is over these sites. So that's a simplification. So then if you go to Australia Plains, Australia, you would have to change this lookup table to reflect this different one out here, this different location. So overall, for the other 3 sites, these tables would not be adjusted. That would be the hope, that we could do that. That for most locations, you wouldn't have to adjust this. But all of this could be argued that, well, we can obtain something from the historic record to put here. So it could just come out of Excel, or you could just have it perhaps based on something else you calculated previously about the historic record. But anyway, there should be some thought put to that. There's probably a more straightforward way to simplify this. So that's definitely something that needs to be looked at. Anyway, so that information then is just applied to WGEN. Here's the WGEN model, and you can see right here in WGEN, here's how we use PWW. And if I open this expression, you'll see it's the this monthly output that comes from Excel. Ultimately, it comes from the preprocessor, right? So this is unchanged, but it's this part, we multiply it by that factor over here, the factors I was just talking about. And so that's how we make drier years dry and wetter years wetter. Same with alpha and beta, they're adjusted in a similar way. And so we talk about that a little bit right here. So this is the change. We also changed a lot in the verification. So we added a lot of precipitation verification stuff. And hopefully this is not something you have to have in your model in production, right? It's a lot of overhead. Maybe you would run it one time for, like, let's say, just put on the shelf and label it as this was a test run to make sure that this model is working correctly for our site, for our location. Once you feel comfortable with that, or maybe you do it for a nearby location where they have more data. And if you feel good about that, then you could apply it to your project and decouple it from Excel, and then just get rid of this verification part because you already feel comfortable with the way it works. So if you can change the inputs and then decouple it from Excel, it will save a lot of time, because it does take some time to communicate with Excel when this runs, and it is an overhead on your model when you paste it in. So to help you with that process, I developed this simple way to hopefully easily transition out of Excel. So Excel is using, or this GoldSim is using this spreadsheet element where it has to connect to all these static inputs coming out of Excel, and then it distributes those throughout the model. Well, I set it up so that I have a container. If I double click on it, it has exposed outputs shown here that all have the same names as what's coming out of the spreadsheet element. They're exposed. When I say they're exposed, it means in another expression, I can refer to any output of that. So let me do it. I just added a new expression. If I type WGEN, you see it pops up the name of the container. This is only because it's localized and it has these exposed outputs, and then it puts a dot. I think there's a dot already there. No, there's not. Now there's a dot. I just put a dot. Here are all of the outputs available that are exposed. You don't get this if they're not exposed. And then I can just use my down arrow key and just walk down through this. If I wanted the autocorrelation that comes out of Excel, then I just hit enter, and there it is, coming out of it's not coming out of Excel anymore. It's coming out of this one. So you can see the only difference then is this underscore. So the idea here is that you just delete this one, and then you just change the name, just open this and remove this underscore, and then reparse the model, run it, or go up here and go to update expressions, F9, and you should see it all connect to this container. That would decouple it from Excel. So anyway, that's how that works. And oh, someone does have a question. Somebody asked, since you only use historical data, you assume a sort of stationary scenario for calibration. What is the credible future window, a reliable one? Yeah, we use historical data to generate not necessarily exact. We don't. It's a lot different than outputting a historic value. What we do is we generate a range of possibilities that are centered on or are grounded on the historic record, but they are all random variables. So, and it provides a range, even a range that could be unique to what we've ever seen before in the past. Perhaps it provides a rainstorm that, or a series of rainstorms that are bigger than have ever been recorded. It could do that. It could simulate that. I bet we would find them because we can run many more realizations than what historically occurred. So I wouldn't say it only uses historical records. It doesn't. It has it provides it's statistically I think accurate or robust. It provides you with possibilities that are, I guess, grounded on historical records. So it's true. If we wanted to look at a possible future that is fundamentally influenced by climate change, well, we haven't addressed that in this process, not at all. But we have addressed at least the possibility of multi-year droughts, whereas before, I mean, they could happen, but they weren't really in the realm of possibility because of the way WGEN was set up. So it's not something we can't drive these long-term deviations from the mean. We can't. We don't have any control over them. But now with this long-term factor, we do. So anyway, sorry, I just want to make sure it's clear we're not just outputting histories here, you know. So anyway, the next question is there an email for questions about this topic? Oh, so what I would say you do is, if you don't mind, the best options are, the best thing to do would be to go to our help center and look it up. So if you go here, you can register or sign in right here. So I'm registered here, you see. That's also good because if you're contacting our technical support, your questions get saved here too, just for you, you know. But anyway, if you don't want to do that, you want to be anonymous, that's fine too. But you should be able to comment on this article. But where I will put this particular model I'm talking about today is in our webinar archive. So anyway, you want to be able to go to the Help Center. So the Help Center is support.goldsim.com. So you go there, and then you go to Webinar Archive, and then you'll find it over here under hydrology. But it's not there yet. You'll find it there when I have it up, and I'll announce that. And then you can comment there. You can also you can just write it in our forum over here. You can go to the LinkedIn group forum, or you can just ask us directly by starting a new. This is by far the best way, because we're trying to um, our our inbox. We're just trying to save our inbox a little bit. We don't want so many emails. It makes it really difficult for us. So if you go here to our webpage, goldsim.com, customer care, go to support, and then you'll see down here, you just click this, online support, submit a request. I know it sounds so formal, and we kind of resisted this for a while. We're like, we don't want to be just this formal bureaucratic company that, so but it just makes it easier for us to keep track of everything and not let things slip through the cracks, because with email, what if someone's CC'd, or what if someone's not on vacation and someone else needs to help, or whatever. Stuff happens. So this makes it a lot easier for us. But that's how you can ask us questions about this model. Just tell us, you have a question about WGEN, and they would probably make sure I look at it. Anyway, so I hope that helps. Okay, great. All right. Well, thank you for joining. Sorry, this went over time a little bit. Thanks for joining. Again, I hope you can make it to the next one. And I am definitely open to questions, comments, feedback about any of what I presented today. Thanks a lot. And we'll see you next month.